Chapter 6, Bending, Part C, Shear and Moment, Example 3. Let's consider we have a cantilever beam with a triangular loading in different conditions. So we call the first triangular loading on a cantilever beam AB with the length of L fixed at A and free at B, loading 1. And the other case is we have the same loading, but the bigger chunk of load is at the closer to the support. So let's go with the loading 1 in in this scenario. To calculate MA, first of all, we can create the summation of moment about point A. And if you do so, summation of point about A gives you considering MA, considering concentrated, considering a moment at A, sigma MA goes to 0, then MA, and consider counterclockwise as a positive moment. So MA minus convert the distributed load of a triangular load of uh, which apply to the beam by convert that to a concentrated load at the centroid. So that applies at 1/3 from the base, which is here, and 2/3 from A. So that's 2/3 of L, and the value is WL over 2. So MA is a counterclockwise moment, and the numeric value is parametric value is WL squared over 3. If you want to draw the shear diagram, so again the resultant force of this distributed load should only cancel by the only support at A. So that means all the load of WL over 2 should cancel by RA, and the same force goes for our shear at the beginning. So we rise we rise up to WL over 2 at the as the numeric value of load is increasing from A to B, the slope of shear should increase. It's at 0 because the numeric value of load is 0 at A. So the slope of shear is 0, which is a horizontal line. Then the numeric value of load is increasing as you go farther to the right. Hence, the slope of shear is, as you can see, it's increasing, increasing, increasing at the maximum at the free end B. Mhm. And if you want to know, because the load was a linear, the shear is a second degree, the load was a linear, mhm, shear is a second degree, and consequently moment is which we already know that the numeric value of moment is WL squared over 3. That's a third degree equation. So in that case, if you want to draw the moment diagram, that's the numeric value comes from the mass. Mhm. And we do know that's a third degree. And also because this is a negative moment, the moment which pushes the top is a negative. So that goes just down. Hmm? And let's observe what's happened to the beam if we just flip-flop the loading. And at the same time, just in case, if we have a parabolic spandrel like y by the equation of y k x to the power of n, the area is 1 over n plus 1 times b times h, uh, which is b is the base and h stands for height. And centroid for that is just b base over n plus 2. So area goes by 1 degree higher, 1 over 1 degree higher, and centroid is goes by. So if this is a third degree, definitely centroid is 1/5 of L. Let's verify that. Yep, that's also the location for centroid. Hmm? And let's just flip-flop the load to see the effect of that on Shear moment diagram. Again, if this is loading 2, the same cantilever beam AB with the length of L with the triangular load of W, but the bigger chunk, as I told you, is at the beginning, closer to the support A. So again, considering the moment at A, summation of moment at about A goes 0, that says MA positive MA minus WL over 2, which is the load times the location of the concentrated load. If we just convert this distributed load to a concentrated load of WL over 2 from the L over 3 from the center, and this is the centroid from the base. It gives us a numeric value or parametric value of moment at A WL squared over 6. So you can easily see how the moment at A is reduced from the previous case, because the previous case, the bigger chunk of load was at the farther end, so creates a bigger moment. And if you want to draw the moment, shear moment, again, RA remains the same. The overall load should cancel by the only support at A, and the same goes for shear. And we just climb by WL over 2 at the beginning of shear, and all of a sudden we just uh, climbs down the road to see. Let's see how that goes. As you can see, the numeric value of load is decreasing to reach 0 at the last. A slope of shear is reducing, and eventually goes 0 at free end B. Mhm. And this is second degree. And the shear, the moment is also goes by likewise a third degree, and we already know what MA is. That's WL squared over 6. And again, because this is third degree, centroid goes by 1 over n plus 2, and that's a times the length. So that's L over 5, that the centroid of the moment. Again, if you want to, for example, from here, the numeric value of a slope is increasing from right to left. So the slope of of moment should increasing from right to left. So that's the best way to double check your drawing or your calculation. Let's uh, overview the effect of internal load. If we want to cut a section, for example, if I have this loading on again on a cantilever being with a bigger chunk of a triangular load at the closer to the support A, and that's a 300 kN over meter, and we want to know what if we cut the section through at C. Mhm. and we want to study the effect of what NC, VC, and MC are at the somewhere in between the two supports. And the length is also provided. That's 2.4 from B. Calculate internal forces, and internal forces are nothing but V's, NC, MC. Moment, shear, and axial force. Let's see how to approach that problem. So first of all, we want to know what sigma c is at what sigma c is. So in that case, if we just develop the relation, when the whole length of 2.4 plus 1.2 is 3.6 meters, that goes by the sigma goes by 300. And what if we stop at 2.4? That goes by sigma c. And then we can easily calculate sigma c is 24 over 36 times 300, and that's a two-third of 300, and that's 200 Newton per meter. 200 kilonewton. Mhm, because that was Kn. And just by summation of forces at x direction, it just gives us a negative c due to the positive of x direction. We can consider that as a positive for our calculation. So negative nc is equal to 0 because there is no other force to cancel. Nc that goes 0, there is no uh, x component of force. Summation of forces at y direction goes 0. That says vc minus the, we just need to again convert the convert the 200 a times 2.4. That gives us 240. Mhm. To cancel by this one, and one of these goes by this one. 240 newtons. I think again that should goes by kn, and that's again 240 kn if I'm not wrong. And again summation of a moment about again this is kn, this is kilonewton meters. Summation of moment about the same point goes by 0. That gives us a negative moment mc minus again 240 times a one third to from the base, which is one third of 24 is 8, and that's zero point 0.8 for 2.4 meter, and it gives you a mc is a negative 192 kilonewton times meter. And that's how we can calculate the internal forces, and also in the two previous, the shear and moment from load. Thank you.